Over the last few videos, we have seen how to model the technology of the firm using production functions and how to solve the cost minimization problem. That allows us to derive what's the cost structure of the firm from first principles. Over the next few videos, we're going to study how to solve the full problem of the firm and characterize how much it supplies at any price, taking those cost functions as given. As you're going to see, there is going to be a very nice interrelationship between the structure of the cost functions and the structure of the production functions that we have just studied. Let me begin with some important basic definitions about the structure of cost functions. We're going to say that there are three types of costs, basically. There are variable costs that we're going to denote by VC for variable cost, which are basically costs that vary with the amount of production. Then we're going to have what we're going to be called semi-fixed cost. Semi-fixed cost. These are costs that kick in if the amount produced is greater than 0, but don't vary with Q otherwise. And there are fixed costs, which are costs that have to be paid even if Q is equal to 0. And of course, that they don't vary with Q, with the amount produced. Now, let me give you an example of what these different types of costs are. So suppose you have a factory that you have agreed on the path to buy the land and the building for 10 years, and you're trying to model what happens this year. So you have agreed to pay the land, and the factory rents the current year. Even if you don't produce anything, you have agreed to pay it. Those are fixed costs. Now, suppose that in order to be able to produce, you need to hire a basic maintenance staff and machinery. So those will be the example of semi-fixed costs. If you want to shut down production, you don't need to hire them for the year. But if you want to produce, you need to have them there. So let me call as example the basic L and K for maintenance. It doesn't really produce anything, but it's necessary to be able to produce. And what are the variables and costs? In this case, it will be the K and L used to produce. That should give you an idea of the meaning of the different terms. Now, given these definitions, we can write the following expressions and define the following concepts that are going to become very useful. We say that total cost as a function of the amount Q produced is equal to fixed cost plus semi-fixed cost plus the variable cost that are produced as a function of Q. Okay? Now, the marginal cost as a function of Q is going to be basically the derivative with respect to Q of the total cost of Q, and this is just basically the derivative with respect to Q of the variable cost at Q. Now, the following concepts are also very useful. One is the average variable cost as a function of Q, which is just the variable cost at Q divided by Q. This is the average variable cost. Average variable cost. Another one that is useful is the average total cost, so function of Q, which is equal to the total cost divided by Q. And if you do the algebra, that gives you that this is equal to the average variable cost as a function of Q plus the fixed cost plus the semi-fixed cost, divided by Q. Okay. Now, let's look at several concrete examples of cost functions that they're going to give us a lot of intuition for the type of firms that we may model and also for how to apply the concepts that I just defined. So the first one is what we're going to call constant returns to scale. That's a situation in which the total cost at any quantity Q is just mu times Q. So there are no fixed costs, there are no semi-fixed costs, it's just linearly increasing with Q, of course, with mu greater than 0. Now, in that case, we can draw the cost function, as a function of Q is just like this. This is total dollars of cost of production at level Q, and basically total cost is just mu Q. So we have a slope mu here. Now we can also plot the average total cost curve for this case, which should be very easy to see. Is just a flat line with height mu. This is the average total cost, in this case the dollars per unit, which is just, remember, total cost divided by quantity, which for this case is just mu. What is the average variable cost? It should also be very easy to see that it's basically the same line. So this is the average variable cost too. Now, why is that the case? Well, notice that all costs here, all total costs, are composed only of variable costs. So if I divide by Q in both sides, I get the same equation. The identity that average total cost has to be equal to average variable cost. Now, a couple of remarks that are important. One is that the type of cost, what is the type of production function that generates a cost function like that, is one in which we can always scale production linearly by increasing the same combination of inputs. So for example, by scaling up the same combination of inputs. So for example, Cobb-Douglas, as we have seen before, with alpha plus beta equals 1, will lead a cost function that looks like this. Now, the second remark that is important is that for the sake of simplicity, I'm just writing you shapes of cost functions, and we're going to be playing with them, and I'm not going to write explicitly how they depend on the input prices W and R. But as we saw from the Cobb-Douglas example, the exact value of the mu in this case will depend on what the input prices are. So keep that in your back of the mind. When we are working with cost functions and we don't specify the input prices, they're always there in the background, and if the input prices change, the exact parameters of the cost function may change. Now consider an example in which total costs are given by a semi-fixed cost that is non-zero plus a variable cost that is going to be linear, let's say mu Q. So it's basically the previous example with the addition of semi-fixed costs. That example is empirically quite interesting because it's the case in which you have to spend some resources to make production feasible, let's say like with the required maintenance or turning on the lights, etc. And then after that, production of every unit of Q has a constant marginal cost mu. So let's draw what this looks like. The total cost function looks like this. This is the height of the semi-fixed cost, and then it's linearly after that with the slope m. Slope mu. This is the total cost. Now let's draw what the different other relevant cost curves look like. So the first one I want to draw for you is the marginal cost curve. And what we have is that the marginal cost curve is flat and equal to mu, because that's just the slope of the total cost curve. The other one that is important to draw is what does the average total cost curve look like. So notice that average total cost in this case is going to be equal to a total cost divided by Q, when if you do the algebra, gives you mu plus the semi-fixed cost divided by Q. Notice that this term is very large when Q is approximately 0 and goes to 0 as Q increases. So if we plot it, the average total cost curve is going to be like this, and it's going to go asymptotically towards mu without ever reaching it. Finally, what does the average variable cost curve look like? That is just the variable cost divided by Q, and in this particular case, it's just mu over q divided by q, so equals to mu. So this is also equal, this line, this horizontal line, to the average variable costs. Notice that this technology is pretty interesting because it's telling us that even though the marginal cost of producing every unit and the average variable cost is the same, because there are these semi-fixed costs that need to be paid, literally the more you produce, the cheaper production per unit becomes. And the reason is because you can spread those semi-fixed costs among a larger and larger number of units. What kind of production function would generate cost functions like that? Well, this is the case of the minimal scales of production that we saw in the section on production functions. And one example, there are many, but we might give you this. So example, it will be a Leontief production function that also has, or with, these minimal scales of production. So you require some resources to be able to start producing, and after that you use a Leontief that will generate this kind of cost function. Again, let me emphasize that the details of the parameters, for example, how big is the cost, the semi-cost that you need to pay, and what is this slope, is going to depend exactly on W and R, the cost of the inputs of production. Now consider another very interesting case in which the total costs are given by the semi-fixed cost plus some variable costs that increase at ever faster rates, let's say mu q squared, just for the sake of the example. So in this case, again, you need to pay some semi-fixed cost to start production, and then every additional unit of production of Q costs you more and more gradually. So what does the cost function course look like in this case? We have that, again, there is the semi-fixed cost, and then you have that the total cost basically looks like this. Is this curve, which is exploding. Now let's draw the other curves as before, and let's start by drawing the marginal cost curve. So marginal cost is the derivative of this, is going to be 2 mu q, so we're going to have the marginal costs are going to be something like this, 2 mu of q. Now let's do what are average variable costs. Average variable costs are just going to be equal to variable cost divided by q, which is basically this divided by q, which gives us mu q. So what do we get? We get that the average variable costs are linear, are increasing linearly, and a line below the marginal cost. This is just mu of q. Now the ones that are really interesting in this example is what is the average total cost, which is equal to the semi-fixed cost divided by q plus the average variable cost, which is mu of q. Okay? So let's think about what happens. What happens is that when q is very large, this term is 0, and therefore average total cost and average variable cost become very close. When q is almost 0, this term becomes infinity, and average total cost is very, very large. It's way up here. So what we have is that the curve looks like this. Okay? And it asymptotically approaches that without ever touching. So this is the average total cost, which is equal to mu q plus semi-fixed costs divided by q. Now, you will notice that I have very purposefully shown that the average total cost curve crosses the marginal cost curve at its minimum. Bear with me for a second. I will show you that that's a general property of this curve. For now, just take my word for it. What kind of technology will produce something like this? What kind of production function can be linked to a total cost curve like this? So an example of this will be a Cobb-Douglas with decreasing returns to scale, so alpha plus beta is less than 1, and some minimum scales of production. That would generate something that looks like this. Finally, I want to cover an example that is widely used in textbooks because it captures many aspects of reality that are interesting. So consider a cost function that looks like this. There is some sort of semi-fixed cost, and then what the variable costs do is first they bend like this, and then at some point they start bending like this. So that's a total cost function. If you want a particular example, just for the sake of being concrete, of something that looks like this, you could have total cost equal to a semi-fixed cost plus, let's say, 1,000 square root of x plus x cubed, where these are the variable cost. That's a function that will have that shape. Now, I want to plot for you what the variable cost, the marginal cost, and the average total cost look like. So let's start with the marginal cost like before. Notice that the marginal cost is very high, then the slope decreases, and then it switches. So the marginal cost in this case is going to look something like this. It's paralleling this. And in particular, notice that they reach a minimum, let's say, somewhere over there. Now, let's think, it doesn't matter exactly what the equation is, you could take the derivative there, but it have qualitatively this shape. Now let's think about what the average variable cost curve look like. So remember, the average variable cost curve is going to be something that is going to cross the marginal cost at its minimum at a point like this. And we're going to have something like this. Again, qualitatively, you can compute the exact average variable cost for this, but it's qualitative that I'm more interested in drawing. And finally, remember that the average total cost are going to be equal to the average variable cost plus the semi-fixed cost divided by Q. So we have the same phenomena that we see before, that the average total cost curve is going to be above the average variable cost curve by a lot when Q is little and by almost nothing when it's small. So we're going to have something like this. And here it approaches asymptotically. Now, as before, notice that I have been very deliberative in drawing the intersection of the minimum average total cost curve with the minimum cost curve at its minimum, and the same for the average variable cost curve. And I will again explain in the next slide why that is the case. Now, what kind of technology has this general shape? Well, it's something, because of the presence of the semi-fixed cost, that has minimal scale, but then it's something that has this notion of optimal scale in the background. Okay? Why is that? Because notice that for a while, adding more production helps, is that you become more efficient for a while, but after you reach a threshold, the inputs of production start bumping into each other and not being as productive, and the costs start increasing very fast again. So it's as if intuitively, locally, you have increasing returns in this region. So this is kind of a region of increasing returns. And I put it in quotation marks because that's a local property I'm referring to, not the global definition that I gave you before. And then you reach an area of decreasing returns to scale. That is kind of the intuition. I want to define and characterize some useful properties of the cost function for the cases that look like decreasing returns to scale, semi, DRS, etc. that we have looked. These properties won't hold in general, but will hold for those important cases. The first property has to do with the relationship between the average total cost curve and the marginal cost curves. And an easy way of describing it is graphically. So ask yourself, what is the relationship between the two curves for any Q? And in particular, let's define a quantity which is Q ATC min, which is the quantity at which the average total cost reaches its minimum. And what we have is that in this region, the marginal cost is less than the average total cost curve. In this region, with Q is greater than this point, Q ATC min, the marginal cost is greater than the average total cost curve, and here they are equal. Second is the same property holds for the average variable cost curve. So let me define Q of ABC mean to be the quantity at which the average variable cost reaches its minimum, and we have a similar relationship as before, the analog in some sense. The marginal cost is less than the average variable cost curve here, is equal exactly at that point, and then here the marginal cost is greater than the average variable cost. And finally, we have the following relationship between the minima of the three curves, which is that the point at which the marginal cost reaches the minimum is less or equal than the point at which the average variable cost reaches its minimum, which is less or equal at the point where the average total cost reaches its minimum. And these inequalities may hold with equality or with a strict inequality depending on the details. Now let's see the intuition for why these first two properties hold. And the best way to see the intuition is to forget these curves for a second and look at the following example. Suppose that I show you a series of numbers, say number 1, number 2, number 3, up to number t, and I compute the mean of them, or the average, okay, of those numbers. And then I show you another number, nt plus 1. Question, will this number increase or decrease the average? I hope you see it very easily that if nt plus 1 is greater than the average, then the average will go up. This is average at t, this is average after t plus 1. But if the opposite holds, so if nt plus 1 is less than the average at t, the average at t plus 1 will go down. That should be obvious to you. Now let's see what this means for understanding the intuition of this. And for example, let's look at this case. So we have that, we have seen for these DRS cases, the average variable cost curve looks something like this. Call this point the minimum. And what I want to show you is why it has to be the case that the minimum cost curve is below here and is above there, which basically means that it has to cross like this, whatever the marginal cost curve is. Now let's see why that is the case. Well, suppose that you are at a quantity Q. What the average variable cost curve is telling you is what is the cost of producing all of these units. And what the marginal cost curve is telling you is what is the cost of producing the next unit. For the same logic that we have seen here, if the marginal cost is below the average variable cost of the previous unit, that's going to pull the average variable cost when we produce the extra unit down. So that is why in this region to the left of the average cost mean, where the average variable cost function is decreasing, it has to be that the marginal cost function is below. What about in this region? Well, in this region, the average variable cost function is increasing. And the only way it's going to be increasing is if the cost of producing the next unit has a higher marginal cost than all of the previous units. So the marginal cost curve has to be above, has to be in this region. The final part of the intuition is straightforward. We know, let's look at this part first, that we have just shown that the average variable cost curve needs to cross the marginal cost curve at its minimum, and therefore they have to cross like that also. We have seen that from this property, but that means that when they cross, the marginal cost curve is increasing, but that means that its minimum has to be to the left. So that shows that. Now what about this part of the relationship? Recall that average total cost is equal to average variable cost plus fixed cost or semi-fixed cost divided by Q. If these fixed costs are 0, the two curves are the same and they must therefore take the minimum at the same point, so this trivially holds with equality. If these fixed costs are not 0, that means that the average total cost curve is equal to the average variable cost curve plus some positive function that is decreasing in Q. Because the function is decreasing in Q, and it's positive, it means that the minimum of the sum must be to the right of the minimum of just this component. And that shows what the intuition, what inequality follows in that case.